So that's sort of our brief tour through important physical properties of solutions. Up to now, we've been talking about homogeneous solutions, right? You can have also what we call suspensions, where are heterogeneous, but if you let them sit for long enough, they'll separate out. Colloids are important. They're heterogeneous, but they do not separate on standing. You can actually get large chunks that are much bigger than single molecules, still relatively small, on the orders of hundreds of thousands of molecules, but still are separate particles. The particles, can assemble. They generally can't pass through semi-permeable membranes because they usually are on the order of tens or thousands of molecules. And you can have both hydrophilic ones and hydrophobic ones. There's a lot of different colloidal suspensions. Aerosols are liquids in gas, like fog. You have water droplets in air, and the fog can stay there pretty much, indefinitely. Solid aerosols, smoke, we're seeing a lot of that. And that smoke will, stay in the air roughly indefinitely. The ash, the heaviest particles, will fall out once it cools enough. The smallest particulates will stay in essentially indefinitely. Foam, you have a gas and a liquid like whipped cream. An emulsion can be a liquid in a liquid, like for example, milk is actually an emulsion of fat globules in water. It's not individual fat and protein molecules just floating around. The fat globules are in water. If you separate out curds and whey, you can see that you have the water soluble component, and you actually have the fat globules that separate out. Solid emulsions, actually opals are water that is dissolved a colloidal water in silica glass. So there's a lot of different colloidal suspensions that have a lot of very interesting properties. One really important colloidal suspension that occurs all the time are soaps. So soaps, fatty acid salt that forms a colloid because of its unique structure. On one end of the molecule, it's ionic. You have an ionic bond. Usually it's a salt, sodium lauryl sulfate. Remember, does that sound like something you might see in a shampoo bottle? It's the sodium and the sulfate are one end of it, and the lauryl, I can't remember the exact molecule is a long hydrocarbon chain. And so you have a ionic head and a nonpolar tail. And so this unique structure allows the soaps to help oily substances be attracted to water. So you've got your ionic head. Oh yeah, sodium stearate is when if you've read your shampoo or soap bottles, you'll probably see sodium stearate in there. And so what happens is you get around greasy dirt particles, you get a colloidal micelles, as this particular shape is called, where the nonpolar tails are surrounding the grease, and then the charged heads are nicely absorbed into the water. So you can get very interesting behavior from this structure within the molecule that is amphiphilic. It has both a water-loving side and a grease-loving side. And a lot of times these mice, since they're charged, they're negatively charged, they can repel each other and keep themselves suspended for longer. Okay, so that is, and one other thing for colloidal particle, again, probably not going to have a question on this, is you get very interesting scattering, that because these colloidal particles are frequently about the size of light wavelengths, they scatter light very effectively. And so you can actually see the effect of the light scattering off of the particles. It turns out that blue light scatters better than red light, and so usually the scattered light is blue. And this is the sort of effect you might see for sun coming down from the sky. That's the Tyndall effect as well, where you see it scattering off of dust or colloidal particles in the atmosphere. Okay, so at the end of the segment, we covered osmotic pressure, and we also looked just a little bit at colloids.